By the way, anyone interested going to UTM? Yeah? We'll have a talk about it. Scary. Why? Huh? So that means you have a very, very strong incentive to go there.
Yeah, try new things. Yeah, I guess
Absolutely.
You were saying about year in industry. What should we do with that? Like, we're interested in that.
Year in industry.
So I mentioned the year in industry.
Go.
Yeah, I applied for that as well.
Absolutely. Do new things. That's why you're here.
But do you know what kind of thing we would actually be doing if we went somewhere like that for a year?
It depends totally on what placement you go for. So you can work in the NHS, you can work for a pharma company, some people, well, there are lots of different opportunities. And it gives you the chance to look into something where you say, oh, I want to know what this looks like, how it feels like, and it's great. I mean, the story about UTM is that the first student that I sent there, together with another student, but that student was about, I think, must be 7, 8 years now. He went there, loved it. They did a lot of traveling then, because if you are there, you know, you go to Australia, you go to Thailand, you do a hiking trip to Vietnam, all these things, yeah, because you are there. But you study as well. He learned Malay. He then came back, graduated with a first-class degree because, you know, you get a total different perspective on life. He then decided that he wanted to go back because he got bitten by the bug, by the Malay bug.
I imagine there's a lot of them out there, so.
Not physically, but, you know. Actually, no, it's not true. I tell this story in the wrong order. He came back, an exchange student from Malaysia came here. Her father told him that he needs to look after her here, which he did.
A certain way.
They became an item. He graduated. Yusra went back to Malaysia. He then went there to teach at UTM English. They got married in Malaysia. I was invited. Fantastic. It was a fantastic event. And he got a job as a science teacher at private school in Malaysia. He is now back with Yusra and Bambini. He has just finished his PGCE and he is doing some teaching in Cambridge.
I thought at one point in this story, sir, you were going to turn around and tell me that, and the whole time this person was, and then you were going to say the name of a lecturer we have.
No,
and it was going to
no, he's not a lecturer. But hey, Ryan, if you hear that, I just told you a story. This is how things happen. But then we also had people who absolutely hated it, who said, you know, I didn't engage. You would usually live on campus there. They decided they didn't want to live on campus, so they moved to the big city, to Johor, which is right in the south. And they said, no, we don't want to use a taxi, we don't go to lessons. Well, what's the point? Yeah?
my father's job, we had to live in Thailand for 3 years, and we just keep going back, and just want to go back all the time. And if I could, I would go back.
We have a placement program with Thailand. Have a chat with your academic advisor about it, if you are set on that. But I would suggest go for something different.
Yeah, because I've already.
You know Thai? Yeah. Do you like the food? Malay food, I would say, is even better. Fair enough. But you know, if people were interested, let me know. I'll see whether we can revive the interaction. Sorry?
Adam's apple.
We're comparing.
He's got a bigger Adam's apple than I have.
Does it matter?
Yes.
Why? Are you one of these size matters types?
No, it's what you do with it.
Sorry.
It's what you do with it.
What do you do? Okay,
Yeah.
fair enough.
Size doesn't matter. It's what you do.
If that is what you do, then
We appreciate that I finally got around to playing my trap shoot. Yeah, but I kept all over them and it took me until like 3 days. I was looking at them, so I really want to play.
right. Kieran is coming back, so we can make a start. Good, excellent. Please don't forget to log in for this second session again. Yeah, I know it's a pain. Somebody in the break just said to me they have already done an Eddie Hofstee plot of the data that they observed yesterday in the practical, and it looks a little bit shite. Well, I'm not surprised. And don't freak out if you've got a little bit of spread out data, because you are doing two plots. I'm asking you to do a Lineweaver-Burke plot and an Eddie Hofstee plot to find the parameters. And what you will find is that your Lineweaver-Burke plot looks much, much nicer than the Eddie Hofstee plot. And that's perfectly normal. The issue is a Lineweaver-Burke plot makes shite data look good. So it is deceiving. An Eddie Hofstee plot makes good data look shite. Right? So that's why a lot of researchers always go for a Lineweaver-Burke plot. The data are a little bit dodgy, but the Lineweaver-Burke plot is so forgiving, it looks really nice. I think this is not the right scientific approach. And the big disadvantage of a Lineweaver-Burke plot is you cannot determine any margins of error. Well, you probably can, but my mathematical abilities are not good enough to do that with a Lineweaver-Burke plot. But you can do that very easily with a Adie-Hofstee plot. So I think an Adie-Hofstee plot, even if the data don't look too great, is better than a Lineweaver-Burke plot. One thing that you should never do with an Adie-Hofstee plot is do not attempt to calculate an R value or R square value. It's just simply in the nature of the Adie-Hofstee plot that an R value, this Pearson correlation coefficient value, is meaningless with an Adie-Hofstee plot. So please don't do it. Okay? Make sense? Don't freak out if your Adie-Hofstee plot is not perfect. Your Lineweaver-Burke plot will look much better. And that's why I want you to do both of them. Right. Now, in this part of the session, I want to discuss with you a strict violation of the Michaelis-Menten equation. Because we said the Michaelis-Menten equation, as we deal with it, has a few prerequisites. Firstly, the substrate concentration must be much, much higher than the enzyme concentration. Secondly, we must not have any product present, so we have to measure everything right at the beginning of the reaction. And the reaction should not be reversible. And the last bit, we said it only works for one substrate, if the enzyme has one substrate. But that hardly is ever the case. So for example, yesterday we used LDH, which catalyzed the reaction of pyruvate plus NADH. And that gives us NAD plus lactate. So here LDH very clearly has two substrates. And these two substrates actually have to come together for the reaction to happen. So technically speaking, we should not use Michaelis-Menten to describe this particular enzyme with two substrates. But most enzymes have two substrates. So how are we going to deal with it? There are different cases. The easiest case, what would be a good example to describe that? Right, yes. We've all been there, and it frequently happens to me. Why, I don't know. Maybe I have done some horrible things in a previous life. You go to a coffee machine, you put your money in, you press latte. What happens? Very often, at least that happens to me, out comes the coffee. 2 seconds later, you get the cup. Have you been in a position like that? Has that happened to you before? Yeah? So you know what I'm talking about. And you think, thank you. Especially when you wear white trousers. So the first case, ideally what you want to have is put the money in, press the button, cup comes, and then the coffee comes. And you take it, and you've got everything together. So this would be an ordered reaction. So we would have, let's say we have the reaction A plus B with the help of the enzyme gives us product P and Q. Like we have here with the lactate dehydrogenase. And in the ordered case, what we are going to have is, we just draw a sort of a timeline, what's happening. We start with our enzyme. We add the first substrate, A. And please note the direction of the arrow. It goes down. So what we get is an EA complex with the first substrate. We then, the second substrate comes in, that's the coffee. We get an EAB complex. This then is converted to an EPQ complex, the products. And again, we might have a strict order. We release P first. Mind the position of the arrow. We have EQ. We release Q. And we've got our enzyme back. It's a very simple sort of scheme that you can envisage here. Actually, that's sort of almost shorthand, and it has a name. It's called Cleland's notation. Cleland's notation, if you see something like that. And very typical for Cleland's notation in this case is that you have a complex EAB. This complex is made up of three entities, of E, of A, and of B. That's why it's called a ternary complex. And it's also called, this particular scheme, ordered ternary complex mechanism. Many enzymes, especially when they use NADH, follow this scheme. Usually you have to bind the NADH first before anything can happen. How can we envisage that? Well, the enzyme has a binding site for A. A binds, and only when A has bound to the enzyme, then the enzyme can also accommodate B. If B comes first, the enzyme says, who the F are you? I'm not going to bind you. You look a bit dodgy. Yeah? So it has to bind A first to get the right conformation to accommodate B. Are you happy with that? Now, of course, if there's an ordered complex, you can imagine there's the opposite. It's not disordered or unordered. It's called random. Now, the best example would be, we can do a little bit of sociology here. How many people here occasionally enjoy a nice cup of tea? Hands up. Nice cup of tea, yeah? Quite a lot of people. Okay. How many people enjoy a nice cup of tea with milk? Hands up. If it is, yeah, right. Now that's interesting. Good. The rest, coffee, brandy, vodka, things like that. Okay, question. What do you put in first? The tea and then the milk. How many of you tea first and then milk?
One doesn't.
Uh-huh. Tea first and then milk. How many put in milk first and then tea? Yeah? Interesting, interesting. There's no shame in it. So if you put in milk first and tea then, what did this used to tell you? A sociologist, at least 50 years ago, where most people followed your approach, milk first, tea then, a sociologist would have had a field day for that. Because not anymore, I have to say, so don't freak out, right? Not anymore. Because usually you get the same result. You get a cup of tea with some cow's juice in it. Did that put you off now?
I mean, I wasn't having it.
Yeah. So what does that tell a sociologist? It tells you about your class. Why? Actually, how would the Queen do it? Tea first or milk first? Milk first?
Lizards don't drink tea.
The Queen does drink tea, I've heard.
She's a lizard.
I'm not getting involved in political discussion. The Queen would put in tea first and then the milk. Why? Right. If you are working class, you can't afford, or you couldn't afford, high quality china mugs. Right? So, if you take a cheap mug, pour in boiling tea, it will go ka-ching. So you put in milk first, the milk cools down the tea, and your mug is safe. So a sociologist would conclude, if you put in milk first and then the tea, you can't afford proper mugs, and therefore you are working class. On the other hand, if you can afford good mugs, obviously you want to show all your mates that you are well off and you can afford a decent mug. Hey, look, I've got a really good mug. I can put in the tea first. I can afford that. And then, I'd put in some cow's juice. So, in a random mechanism, actually, it doesn't matter which way the substrates arrive. Let's say we have enzyme, and it can go either way. We can have A first, where we have EA, then we have B, where we have EAB. This is converted to EPQ. We release P first. We have EQ. We release Q. And we end up with our enzyme. Or B arrives first. We have EB. A arrives second. We have EAB. It's converted to EPQ. We release, say, Q first. We have EP. And then we release P. And we have our enzyme back. So this would be a total random. We still have a ternary complex mechanism here. It basically doesn't matter which ones comes first. Are you happy with that? And because all good things come in threes, we have another mechanism which is totally different to that. I'm not giving you the name for it because you have to find out the name yourself, how you would call that. We have enzyme. Here's our timeline again. We have A. Which gives us an EA complex. Now the enzyme converts A into P. And it gets sort of modified. And I indicate that with this sort of dash. And P is released. And we have our dash enzyme. Now B comes along. We get E prime B we convert this to EQ. Note that this E no longer has the dash. It has transferred whatever it was onto B and converted it into Q. Now we can release Q and we've got our enzyme back. Can you see what's happening here? Do we have a ternary complex at any point where we have EAB? No. This is a total different mechanism. think of a nice name for that. It's a sport, actually.
Ping.
Loud!
Ping pong.
It's a ping pong mechanism. You're absolutely right.
Seriously?
I'm afraid, Alex, it's ping pong.
That was a complete guess.
Well, obviously a very educated guess. It's called ping pong. You do not have a ternary complex in a ping pong. Very often you will find that enzymes that use ATP make use of this mechanism. They bind ATP first. The ATP transfers a phosphate residue onto the active site of the enzyme, and ADP is then released, and the phosphorylated enzyme waits for the second substrate to come in and transfers the phosphate group then onto the second substrate. So, for example, we can use the example of this is sort of my shorthand for a molecule that we will deal with a lot soon. This is glucose. And each dot represents a sugar. 1, 2, 3, 4, 5, 6 represents a carbon atom. So we have six carbons. Glucose plus ATP. In the first step of the glycolysis pathway, glucose is phosphorylated in the 6th position. Like that. And that would be glucose 6-phosphate. You usually see that abbreviated as G6P. Absolutely essential reaction. Without this reaction, there would be no life. And we will discuss that probably next week or the week after, why this is the case. This transfer is catalyzed by an enzyme that transfers phosphate from ATP to its substrate, and obviously we generate ADP. And usually enzymes that transfer a phosphate from ATP that do this reaction, they're a little bit unusual because they have unusual names. This enzyme here is called hexo because it works on a 6-ring sugar, hexo, and it transfers phosphate and enzymes that transfer phosphate are called kinases. So this beast is a hexokinase. So kinases usually, very often, sometimes, work through a ping pong mechanism. how can we distinguish between the ternary complex and ping-pong mechanisms? Between ternary and ping-pong. Because sometimes we really want to know by what mechanism does our enzyme actually work. I have to say, with these methods, you cannot distinguish between an ordered or a random ternary. You just can distinguish between ternary and ping-pong. What you would do is, you would do your experiment exactly like you did yesterday. You take a fixed concentration of B. Let's say 10 millimolar B. And you vary your concentration of A, like you did yesterday. You did that with a fixed concentration of NADH yesterday. You did not modify the concentration of NADA. You just changed the concentration of the pyruvate. And in a line-Weaver-Burke plot, what you would get for a ternary complex so that's at, say, 10 millimolar B. You get a straight line. Now you do the same experiment, but with a different fixed concentration of B. Let me just quickly redraw that. B, let's say 20 millimolar. B, 30 millimolar. What you see is, if you increase B, your line-Weaver-Burke plot looks a little bit like a sort of a hand, a fan or something like that. Has a fan-like structure. That is indicative of a ternary complex, if you see something like that. So that is ternary complex. If you did the same experiment with a ping-pong enzyme, you would see something like that. The lines are parallel. That's why I've chosen a line-Weaver-Burke, because it's easier to remember. Ping-pong parallel. Just make sure that nobody is standing in front of you when you say that with a hard P, because they go like that. Yeah? So that is how you could distinguish between ping-pong and ternary complex. But actually, if you think about it, there is also a different way of dealing with that. how you can very easily, experimentally, distinguish between the two. Let's look at the two schemes together. And it doesn't matter whether it's ternary ordered or ternary random. What happens if we have enzyme and, let's say, substrate A in the case of a ternary complex? Well, the enzyme would bind substrate A. And then, well, basically that's it. The enzyme sits there waiting for B to come. Nothing happens. That's ternary. In the case of the ping pong, what happens if the enzyme binds A? Well, we modify the enzyme. So we would get a modified enzyme, and we also release the first product. So in order to find out, is it a ternary or is it ping pong, all I need to do is take the enzyme, add the first substrate, and see whether a product is released. If the first product is released without the second product being present, then I know it's a ping pong mechanism. Yeah?
What if you don't know which substrate comes first?
You mean if it is an ordered mechanism?
No, it's a ping pong reaction.
Oh, ping pong.
You don't know
Ah.
you need to put the A or the B in.
Good point. If I don't, yeah, it could very well be that I don't know what goes first, either A or B, but it's very easy to find that out. I just do an experiment, enzyme plus A. Does it release anything? No. Okay, enzyme plus B. Does it release any? Oh, look, hey, cool, yeah, wow, whoo, yoo-hoo. We release P. So I know that in this case, it would be B would be the first substrate in a ping pong mechanism. Make sense? Very often, what we can do is we can actually isolate this guy here. Or rather, wait a moment. No, we can't isolate this guy here. We can isolate this guy here. The modified enzyme in the ping pong. We don't have a modified in the ternary, so we can't isolate anything here. This modified enzyme, for example, a phosphorylated enzyme, is potentially stable, and therefore it can be characterized. You don't have this guy in the ternary complex. So in theory, it is pretty simple, and experimentally it's not terribly difficult, to distinguish between ping pong and ternary complex. Are you happy with that? Now, Clapper is known for occasionally throwing a total spanner into the thinking of students, especially in exams. So occasionally asking for the Cleland notation of a ping pong enzyme or a random ternary enzyme. And a lot of people fell over because they thought, oh my God, we need to do something really, really complicated. No, you don't. Clapper doesn't want to trip you up. Clapper doesn't mean to be mean to you. If I ask you for a Cleland notation of a ping pong enzyme, all I want you to do is write that down. And if I give you a special reaction, for example, here this one here, the hexokinase, all I want you to do is say A equals ATP, B equals glucose, and then you do this thing here. Show me that. P equals ADP, Q equals glucose 6-phosphate. You just do a little legend, what's what. Make sure that your arrows are in the right directions. You get full marks, and life is good. Can you do that? Any questions? This is actually quite advanced enzymology, but I thought I can do that with you because you can handle it. No questions? Don't forget to do quiz 2, 16th of February. Enjoy life!